Oh, get your phone because we got to.
Recap a piece
I need
of
to
that
check.
giant bread.
Okay, that's what I'm trying to do here as we start the show here, folks.
Giant, like
there.
Baguette bread thing from Panera Bread. And I
Yes, late lunch
singing,
once again, folks. How's everybody doing out there?
Piece of giant bread for Joey. And then Dad related
wait, Joe, before you drop your sandwich, go sit and have your stuff. As you know, it's never a dull moment around here, folks. Welcome once again to our live streams here. Our final week as we enter here, week 10.
Oh.
And yes, yourself. Okay.
No.
Good to have you guys here or whatever.
Like the French thing. That's better than
Not quite.
mine.
You know the deal of how this works, however. Live chat is open here. We're ready and waiting for any requests that you guys have for math topics or whatever. And just give you there just as a reminder so you can see it. You know at the what are you typing now? There. No, wait, what are you doing?
That's true. You want a little cup or you want that?
Oh, you're giving this to me?
Yes.
Oh, I got you. Okay.
Hi. Really?
Yeah.
That makes sense.
How clever. Anyway. All right. While we wait for some visitors, maybe perhaps our international friends that have been joining us in recent goings on, stuff like that. Okay, all right. Enough.
Okay.
Enough for around the chat. I got some questions for you to make up for not being here the last time and stuff like that.
I was here the last time. A little bit.
I meant when there were certain questions that I wanted you to help me with, and you decided to literally take a powder. So, figure of speech. You guys out there know what I mean.
Oh yeah.
Just
Because you said literally. I'm like, what? I wasn't eating any sugar powder. Fungit powder.
Okay.
Baby powder.
Last week I was talking about I was trying to start for my geometry guys discussions about arcs and wedges and stuff like that and things like that. I had talked
that slice of pie.
I had talked. Okay, well let me ask you this: if this wedge is if this central angle in the middle of the circle is 55 degrees, Brianna, how many degrees would this arc be right there? If this angle in the middle of the triangle, in the middle of the circle is 55 degrees, how many degrees is that arc?
Well, the rest of it, wait.
Well, think out. How many degrees is the whole thing?
360.
All right.
15. The rest of it would be 15. I mean, not 15. I mean 315.
Oh. Wait, not 315. Wait, 60 minus 55 would be.
Oh wait, no, just 305.
Okay, well the rest is 305. But again, what I showed last week was that whatever degrees the center of the circle it is in the center of the circle, Brianna, this piece, the arc.
I'm cold.
Wait, Brianna, stay with me. Stay with me. Brianna. Okay, Joey. Yeah, that's true. Okay, no, I know what she's saying. So no, but how many degrees is the arc? This piece of it, yeah, it's also 55 degrees. Okay, all right. Now I want to expand.
Question.
No. Well, in a sense, it kind of is. Okay, really? But yeah, no, they match attention. No, wait.
Oh yeah, it tricks you because it makes the person would think, oh, it's a trick question. It can't be 55. But the trick part is that it's actually 55.
Right. So don't think. Yeah. Now, I want to expand upon one thing from last week because there was something I wanted to talk about last week that before we had questions come in that I know some of my geometry guys are doing this and you guys out there might be doing it as well with this. But we talked about major and minor arcs on Friday. We did the whole thing. I want to expand one little thing. These arcs can also be useful for the purpose of identifying what the actual linear measurement of this arc is in relation to the whole circumference of the circle. All right. Suppose just for a second.
Wait.
Wait. Not yet.
Does this
Wait,
start?
wait.
So this
Give me my
one's
bit
lower.
first. Wait, give me my bit first. Brian, let's suppose that the radius of the circle was 3 centimeters. Okay, we talked before. Do we bring up circumference before previously? I thought we had talked about it before.
I think so, yeah.
Okay, we said that the circumference of a circle is measured by 2 times the great Greek number pi times the radius. That, yes. Well, again, we know the deal with pi. Okay, but don't use that marker. It's dead. So if they give you a circumference of 3, okay, Brianna, you can't even see it.
You can't?
The marker's dead. It's practically, yes, I know we have new markers. Okay, yes, hold on. We'll get them in.
I can draw my pie.
Chill. Stay with me on this first.
Well, yeah, you can barely see that on camera.
Rewrite the formula, but put the 3 in. Wait, rewrite this formula, but put the 3 in.
There we go.
No.
What?
What does the 3 take the place of?
The pi?
No.
The 2?
The pi? No.
The C. The C.
No.
The R?
Yeah, 3 is the radius.
Oh, that's what radius means.
Yes, okay.
That's what radius
but put the 3 in the parentheses, though.
Oh,
Now,
that's what the R meant.
all these are sitting next to each other. What operations do we do with all of them? When they're sitting, okay, so let's get the 2 times 3.
6.
All right, so 6. All right, so 6 equals 6 pi. Now let's actually calculate that and see what it comes out to.
Like that?
No, wait, 6 times pi.
Oh.
Okay, so we punch it in. Okay, and it gives us approximately, rounds it to 2 places, gives us approximately 18.85. Okay, so 18.85 centimeters.
19.
No, wait. Let's use, okay, 18.85 centimeters because of that. Okay, now, that's the circumference all the way around the circle. Now, the thing is, how much of that 1885 is covered just... Okay, all right, chill. She's never going to let the pie gag go, folks. Okay, wait. So here's the thing, Brent. So the thing is,
that little squiggly looks like the rim of a pie.
Yes, it does. Furthering the point. Now, here's my question, though, Brent. 18.85 centimeters, that's the distance all the way around the circle. But how much of that 1885 is covered just in this 55-degree arc? The question is, how can I get just that piece? Okay? Because you know what the circumference is. Go ahead.
Pie, you cut it. You cut the slice out.
But wait, this is wait. Well, wait, hang on a second. But wait, hold on. We can get some of that because this is 55. This is a 55 piece out of what? This is 55 out of
360.
Right, exactly. So watch this. If you take that angle measurement, in this case the 55, divided by 360, that tells you. This fraction tells you what part of the entire circle you've covered. So if we take the 1885 that we just got and multiply this fraction into it, that will give us what is called the arc length. So let's just expand upon the thing. We've still got the 18.85 there on the whole business or whatever. Bring it over here. And let's just immediately hit a times 55 divided by 360. Helps if you use the exact number. Just don't use the rounded answer that we got. Just carry the raw calculation in your calculator. Just bring it over. And it comes out to that just this 55-degree piece comes out to about 2.88 centimeters. That would be just the direct linear measurement of that. So every arc.
The lemonade. The Livestream has been saved from being thirsty because I have brought the lemonade.
Very good, thank you.
Lemonade, yay!
All right, so every time you come up with every time you have an arc, you can get 2 measurements out of it. Both its degree measurement. All right, come on, Brianna.
Sorry.
You keep talking over me here. Stop doing that. So every time you come up with an arc, based off of the central angle, you could always come up with two things. You can come up with its degree measurement, and you can come up with its linear measurement by seeing what fraction of the entire circumference that it is. All right, now here's my next question to you, Bria. Let's get a little more. Let's change the bit a little bit. Okay, we've already stressed that when you have a 55-degree angle in the center, that it's going to give you a 55-degree arc. But now, what if, notice that the corner of the angle is here at the center of the circle. What if instead of it being in the center right here, what if the end point of the angle was also on the circle someplace else right here? Now, what degree measurement would you say that this angle is? I'm going to give you a hint. It's not 55. This angle is not 55 degrees anymore. So how?
Because it's longer.
Okay, but well, it's pulled back farther.
Yeah.
The fact that it's pulled.
Must like
wait. So here's my question. Given that the fact the angle is pulled back farther, look at the size of the opening. Does the size of this opening angle-wise look bigger or smaller than the original 55? Does the width of the opening look bigger or smaller? Yeah, I can't translate.
Bigger.
Huh?
Bigger.
Okay, wait.
Because it looks like, originally it was like a Pac-Man, but now it's like Scissor Man Scissors.
Cut Man Scissors.
Oh, Scissor Man.
Okay, no.
I thought it was Scissor
Cut
Man.
Man is his name from Mega Man. No. Okay, but here's the thing.
So the opening is bigger.
No. Actually, it's not. I'm talking about the width of the opening, not the length of the lines that make it. The width of the opening here.
Oh.
Like I said, look, here you've got this. Down here, you've got this.
Oh, that makes sense.
So you see that it's a smaller opening now.
That makes sense.
So that means this angle's got to be smaller than 55. The question is, how much smaller? You're going to see that it just involves one simple calculation, okay?
Mm-hmm.
Think about this. We talked before. The radius that you have here. You have the radius, and then you also have. We talked about segments like the radius like this. We talked about segments like the diameter like that. How much bigger is the diameter compared to the radius?
That's cut all the way.
What? So wait, how much bigger would this be compared to that? Like before, if our radius was 3, what would the diameter be?
3?
No, diameter would be 3. The radius and the diameter aren't the same. Say it.
6?
6, yeah. How does 6 compare to 3?
It's 2 times
more. It's twice as big. So this point is in theory, and I say in theory because what you'll see is that it doesn't matter if this point has been pulled back exactly from the middle of where that is, or if it's pulled in this direction, that direction, whatever the case is. That theory of it being twice as far away lends itself to trying to come up with this angle. How do we counterbalance a times 2? Divide by 2. So what you're going to see is that this angle right here, what we call an inscribed angle in a circle, is always going to equal half of the arc that it captures. So what is half of 55? Get that, and you've got get that half of 55, and you've got your what the measurement of that angle is supposed to be. You guys have it out there?
27.5.
27.5. Bingo. That's exactly what it would be.
You said inscribed.
No, okay. The reason why it's called inscribed is because the entirety of the angle is physically drawn inside of the circle. Okay? And that's a general concept that you hear a lot within geometry related sort of things. The idea of inscribed and circumscribed, and some people get those two concepts confused. Just to explain.
No, that there's.
Okay, wait. Well, no. Wait. This is important.
Like all morning, I've been hearing you say inscribed. I'm like, he's talking about epithet or race, isn't he? Because that's the word. If you have an epithet, inscribed.
No.
I don't know. I
don't
might
even know
just
what you're
be
talking about.
dumb and forgetting.
No, stop. No, you don't. You're not doing anything wrong. No, you just.
No, but it says that.
A, I don't know what you're talking about in the first place, and B, no,
it's
you're
the
just.
show that Yellow Apocalypse played. You know, with the with Molly, the hair.
Again, I don't watch that show. You do. But here's what it means about whenever you're talking about something that is inscribed versus something that is circumscribed. Okay, here's the main difference between those two things. Follow along with me for a second. What it means for something to be inscribed within another figure. Okay, Brandon, what are you doing? Pay attention. Stay with me here.
I'm trying to draw Molly.
Stop. No. But, come on.
Okay. Sorry.
So here's the thing. What it means for something to be inscribed inside of a circle or any other geometric figure, but usually we use this concept with circles, with angles and stuff like that. The idea is that you have a figure that is completely contained within, that you draw a figure completely inside of another one, and all of the endpoints of that inside figure touch the edges or whatever of the figure that's inside. So like here would be an example of an inscribed triangle within a circle. Okay? This triangle is considered as being inscribed because all three of its endpoints are located on the circle and connected in. So basically the circumference of the circle completely touches every part of the triangle itself. So that would be an example of a triangle that would be an example of a triangle that is inscribed in the circle. Now here's what it means for a triangle to be circumscribed. Wow. No, wait. I'm busy here.
Sorry.
Do you notice I'm still talking and making a point, Brianna?
Oh. Well, yeah.
Now here's an wait. You gotta move that because no, because
you will be missed.
No, I need the space. Okay. Now here's an example. Follow this. Here's an example of a triangle that is circumscribed. Now, fitting kind of the definition of when we call this the circumference. Circum means to go around. So when you circumscribe something around another figure, that means to draw it in such a way that it's on the outside of the figure that you're starting with. But still, in the process of drawing the new figure around the other one, it still touches the figure in every possible direction that it can. So here's an example of what a circumscribed triangle would look like.
Since the triangle is inscribed, he's saying, I'm special.
So,
because he's special.
So there's an example of that's an example of a triangle that is circumscribed or drawn around, but still touching the circle. Okay.
Now the circle is saying he's special.
And then here's an example of a square circumscribed around a square circumscribed around the circle would look like that. Whereas a square inscribed,
those new markers?
A square inscribed in a circle would look like that. So you see the difference. In means it's inside, completely inside the other figure, but touching. And circumscribed means it's drawn around the figure, but still touching everywhere. That's the difference between the two. So that's the reason for this name. So the inscribed means the angle's drawn completely within the. All right, enough. Are you gonna keep talking over me? I don't mind the awkwardness, folks. No. Okay, all right. Listen, I apologize, but no. And I admit this is a personal thing with me or whatever. I don't mean to get this to mess stuff up. But understand, I'm trying to explain things. I got to hear myself, and I got to make sure that I could follow and explain myself properly or whatever. I want to make sure I'm hearing myself so that I don't mess up. When I'm hearing two voices at the same time constantly, that messes me up. Okay, so I gotta focus. All right, enough. Can we get back to the point? So that's what it means for the angle to be inscribed. Okay, that means it's completely drawn within the circle, and all the 3 key points of the angle are touching the circle. And like I said, the measure would be half the arc. So just to play it out again, what if what if I gave you the information the other way around? What if I told you that the angle was, let's say, 35 degrees? How much would the arc be? Wait, if the inscribed angle is half of the arc, so how would you get back to the arc?
Well,
wait, no, wait. The 35 is the half. You're thinking it's 17 and a half anyway. But like I said, the angle is the half. So then get back to the arc. So how do you get back to the arc? Yeah, it would be 70. Yeah, because you have to take double. Yeah, so this is the half, that's the double. So you got to recognize what direction you're playing off of in every given circumstance and things like that. So that's the nature of that. Okay, now I got it. Now I want to ask you this question. Okay, this is important. Follow me on this. Okay, now expanding upon this definition. Here's a question for you. Okay, remember a second ago we were talking about the diameter, Brianna? Okay. So let's suppose you have the diameter of a circle. Okay, now, here's what I want to know. How many degrees is this arc right here? Brandon, yeah, look at the picture. How many degrees is this arc made around the circle like this?
180.
And why would it be 180? Talk up. Come on.
That's half of 360.
Yes. Okay. So you notice 180 degrees. So then let me ask you this. If I were to draw a triangle here in the circle, and that triangle uses the diameter as one of its segments. So if I inscribe this triangle in the circle and I use the diameter as one of the lines in the triangle, how big is this angle right here? How big is that angle going to be right at the bottom? It's always going to be one specific thing. No, wait. Remember what you just got up here, the 180? Look at the lines here. This line for the angle captures this point in the circle, and this line that makes up the other part captures this part. These two make up the diameter. You just said the diameter was how much? 180. So that means that this arc is captured by this inscribed angle, which means how much is the angle going to be? Guaranteed. No, this wouldn't be 180.
Oh.
What's that?
90.
Yeah, it's 90. It's guaranteed to be a right angle. It's guaranteed to be 90 degrees. So any triangle inscribed in a circle that uses the diameter as one of its sides is guaranteed to have a 90-degree angle because it's going to capture 180 like that. So that's the nature of that piece. So just a little something extra there for you guys to wrap your head around and make things a little bit easier for yourselves. Hopefully, perhaps, maybe. So okay, what do you need? What do you need? Just tell me. No, we're not playing charades here. Come on. Not that you guys can see it, but regardless. All right, just what do you need? Just go tell me. Tell me. What do you need?
Can I get something?
Quickly, get.
Yeah, that's what I was trying to say. See, I was pointing to myself. I was doing this, and I was doing it back. See? I'm gonna go get something.
You could say something.
Well, I didn't want to interrupt you.
I know. All right. Well, I'm hoping I don't have to do this like a classroom, especially last week, and have a raise your hand or something. And even down to the end, we're being crazy. We hope you are too, but we hope you're learning something as well, okay? Because we're committed to that here, and we want you guys to get what I'm trying to have you guys get out of it. Okay, now, all right. Now at this exact moment, okay, our visitors from last week, they're not here at the immediate moment,
Totally can't see what's behind my back.
Will you just sit and put your hoodie on?
Can't see what I have.
All right, now,
Uninvited my
I wanted to make a point. All right, now, I wanted to make a point that on Friday, when our friends from the Netherlands were by, I remember we were doing a lot of stuff about scatter plots and stuff like that, and they were asking the question of.
Oh, that reminds me of the thumbnail. Look with the falling fruit, and it like makes a weird shape.
Again, why do I have you do these things? Okay, so here's the thing. One of the things that they were asking me about last week that I promised them I would get to in this show. So so guys, if you happen to see this later, I hope that I hope that you take a look at this. I'll put the timestamp in later and stuff like that. One of the things that
I'm a bird. This is my beak.
Rana.
Just struggles to get into your hoodie.
Here's what I did. Before the show today, I took a look at the scatter plot that I made last week because for the purpose of trying to come up with, because the main thing that they were asking me about, folks, was about correlation, trying to calculate the correlation of the data in a scatter plot to see how close to it being linear it's actually supposed to be. Because we said last week the scatter plot that if a series of points in a particular set of data perfectly makes a straight line, then it has a correlation coefficient of positive 0.1 or 100% related if it travels in a positive slope. If it travels in a negative slope, perfectly in a line, that would be a negative.
If it travels at a neutral slope.
Okay, that's something I actually have to look. I have to actually look at that for myself, because I described when a series of points has no correlation whatsoever. That means that they are fully, totally scattered in, with no complete direction. No, wait.
When I said neutral slope, I meant like it's just a line down the middle of the L.
Like this would be having no correlation whatsoever because there's no definitive pattern or direct. There's no definitive direction or anything to the points. No. I know exactly what you're talking about. If you're talking about something that has a zero slope like this.
That's a thing?
Yeah.
Oh.
Because think of it, zero grade or all that kind of stuff. Yeah, it starts on the flat.
There a thing has zero grade
edge? If you want a positive slope, you have to start ascending upward. If you want a negative slope, you have to start descending downward. That's exactly how it works. Okay, but I'm going to be honest with you. A line that has a zero slope, I actually have to look at that for myself and see, how do you describe if a series of points makes a perfectly zero slope line like that and doesn't scatter off of it? What's the correlation of that one? because I don't necessarily think it would be a zero slope. I would probably akin it to a 0.1, but or one whole rather. But I'll double check that and get back to you. So I'll have to take a look at that. But anyway, back to the point that I was making now. Okay. The thing is that as far as calculating the correlation coefficient of a scatter plot by hand when it's not perfect or whatever, I'll be honest with you. I thought it was harder than it actually is. There's still a lot of calculations you got to do, but I tested the graph that I made up on the fly last week when our friends from the Netherlands were asking about that stuff, and I want to reintroduce that. I'm not going to redraw the graph, but here's what I did, and I did this a little while before, and I did this a little while before the show. I took a look at the graph that I drew and the 10 points that I drew in that scatter plot. Now, let me just look at the list again real quick. Okay, here were the 10 points that I drew in that thing. I drew 1, 2, 2, 2, 3, 1. Yeah, these were the 10 coordinates of all the points that I graphed there. I had 4, 3. All right, here, Brianna, can you do me a favor just so I can do this faster so I don't have to keep looking back and forth? Just all right, start from 4, 3. Read the numbers on
5, 4.
5, 4.
6, 5.
6, 5.
7, 4.
7, 4.
7, 5.
7, 5.
9, 6.
9, 6, and
10, 6.
10, 6. Okay, so these were the numbers that I drew. Okay, now.
54,
So now, wait. I'll explain what those are in a minute. Now, using those 10 coordinates, here's how you calculate the correlation or the closeness of all the points to a straight line in a scatter plot. So the way you do it is this. You start by taking, there are several additions and other calculations that you're going to have to do. The first thing you're going to have to do is you're going to have to take all of your x coordinates and all your y coordinates and get a sum of each group. So according to calculations that I did.
That's a 7 and not an 8. It's 7, 8, 9.
So all of the x's hot. So all the x's when added up, they came out to 54.
Oh, that's why those numbers.
All the y's when added up, they came up to 38. Okay, we're going to need those numbers in a little bit. Okay, and there's going to be some symbol notation that we're going to use to represent these numbers, because there is a Greek symbol that's used to represent the sum of a set of data. We'll introduce it in just a second. Some of you that are doing higher level math have seen that before, but you'll get the idea.
Dad, I know why you didn't put an 8, because 7, 8, 9.
The 9 wouldn't be there. What? The 7, 8, 9, the 9 wouldn't be there because it would be eaten.
Oh.
Yeah.
No wonder there's no I for 9.
Now, there's 3 other calculations. Now, to calculate the correlation coefficient, there's 3 other calculations that you have to do. All right. The first one you have to take the x and the y in each point and multiply them to each other. You also have to take the x and square it and take the y and square it. Okay, so here, Brianna, here you help me out with this. Okay, let's so here let's make sure this works. That doesn't work. I know. I have a new set markers. I know.
Sally's coming
okay,
for a
but
cookie.
I'm trying to save myself from having to use it right away, only because I'm also using the fine tips. So let's okay.
Those are fine tips?
Well, the thin ones here. Okay. I also want to make sure I'm picking one that's invisible here. Okay, all right, so use it. All right, so you use this. Okay, here's what I want you to do.
Yeah.
While I list all the x times y's and all this, you take all the y coordinates that you see, Brianna, here and square them all. Put those results here.
Square?
Yeah.
That means times by 2, right?
No, not times by 2.
4?
You multiply 2 of that number. So you multiply 2 2s, 2 2s, 2 1s, 2 3s, 2 4s. Okay, give me.
I forgot.
Okay, give me that information.
2 2s, 2. So 2 times 2?
Yes.
That's 4. 2 times 2. 4 again.
And I'm going to multiply the x's and y's together.
3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 4 times 4, 16. 5 times 5, 25. That's like a
25. So, see, always proofread your work. Just because this is a math course doesn't mean you don't have to use reading skills. Okay, all right, and then do the same thing with the x. Do the same thing with the x squareds. Okay, so square all the x's now. Okay, and once again, we'll get a total of each thing. Okay, so now square 1, square 2, 3, so on down the line.
So
okay, these.
1. Oh, sorry.
It's okay.
4, 9.
So the thing don't crash and burn. It's fine.
16, 25, 36. Yeah, my handwriting on a whiteboard is
You're angling yourself. That's why.
49.
Okay.
25.
No, wait.
Oh no!
That's the y squared. Watch.
Again.
49 again.
81.
10 squared would be.
10 times 100.
Okay. Grand total of that of all these comes out to 370. Okay, so all these sums are important to us because it's through the use of these 5 numbers that you calculate the coefficient.
Oh, wait,
again,
I know what they turn into. A huge cookie.
No.
Yay! Cookie! Big cookie for everyone.
Here is the formula.
Here's your cookie, guys.
Here is the formula that you need.
Your cookie. Click on the cookie to get the cookie.
For a correlation coefficient.
If you clicked, hooray! You clicked on this cookie. Hooray!
For the correlation coefficient, here's the formula that you need to use. Now watch, because there's a lot going on in this formula. So ready for this. Here's what ends up being. Okay.
I'm ready.
Okay. You start with n. Now, in our past formulas that we've seen for other things like that, n is always represented the number of items in the set. So, like for instance, in this table, how many ordered pairs do I have here, Brianna? How many ordered pairs do I have here? How many points do I have? 10. So in our case, in our example, n is 10. But n is going to always be whatever number of items you have in the data. Okay. So you have to take that. You have to multiply it by. Here's our Greek symbol. This is the Greek letter sigma, and it's always used to represent the sum of a set of data. Okay.
Mm-hmm.
You have to take the sum of the xy numbers. Okay. So it's n times the sum of xy. Okay. Minus. Okay. And I just want to make sure. Okay. Minus the sum of the x's times the sum of the y's. Okay. So you have to get all those. Now that's just the top half of this formula. Actually, I'll tell you what. Here, wait. Now that I've explained this, here, wait. I'm going to take the sigma out because let me write this as a fraction because, all right, yeah. When I read the formula earlier today, it had it as one long string horizontally. But since there's a division, I should probably write it as a fraction to simplify it a little bit. Now on the bottom is one giant square root. What's contained in this square root is the following. It's the product of n times n times the sum of the x squared terms minus the sum of the x terms squared. Now notice the differences in how I said that. The sum of the x squared terms and the sum of the x terms squared. There's a difference there. And that gets multiplied by, and I got to extend my fraction bar, n times the sum of the y squared terms minus the sum of the y terms squared. Again, difference between two. So you do all this, you do all this, you multiply those together, and then take the square root of the whole thing. That's the entire division of what you get to the top. So that's where all these numbers and the 10 get plugged in. You just got to pop them into their appropriate places in the sum. So in this circumstance, then, for instance, okay, on the top, you've got that n is 10 times sum of the xy's was 248. Okay, minus sum of the x's was 54 times sum of the y's was 38. Okay, so all that's on the top. Now for the bottom, here's our giant square root here. So let's see, in the first parentheses, it's 10 times. Sum of the x squareds was 370 minus the sum of the x's was 54, and we have to square that. And then the next one, it's now with the y's. 10 times sum of the y's was 172 minus sum of the y squares was 72, and then sum of the y's 38 with a square there. Okay, so this is everything you got to punch in. You got to put all this into place there within your formulas. So I'm going to strongly recommend have some kind of a scientific calculator so that you can sort all this out and all that business or whatever. Okay, so let's see if because I did this all on a spreadsheet earlier today. I'm going to see if I can punch this all in by hand and just make sure that it comes out in place there. Okay, so let's see. So 10 times 248 minus 54 times 38 parentheses. Okay, divided by square roots. Where's square root? Okay, square root. And now in the big parentheses. Okay, I set up a double parentheses so I can do this. 10 times 370, okay, minus 54 squared, close, open, 10 times 172 minus 38 squared, close, close. I should have to do a double close because I started with a double open to make sure everything was under the square root. Okay, everything looks the way that it should. I will hit the equals, and let me see if this gives me the same as the spreadsheet said, and it does. So after all that calculation, the correlation coefficient that we get ends up being 0. Approximately. We'll call this to two places, about 0.92. It's just a very small shade above that, ever so slight. But what this means is that so the correlation coefficient is a positive 0.92. That means that these points are very closely knit together, almost a perfect straight line with each other, and traveling at some kind of a positive slope. So I'll be honest with you. The calculations themselves, there's a lot of them to do, but the calculations themselves, because you're just taking numbers and either adding them all up, multiplying them to themselves or each other and adding those up, getting these numbers is actually pretty simple. And this gets into something that, and I know I've told you about this before. I've told my students about this. I'll tell a lot of you guys at the same time, and this is the truth. Okay. One of the things that you learn over the years, the more as you get into higher grades and you start doing these types of calculations and problems more and more and stuff like that. The thing you learn after a while is that the type of stuff that you do within math, you could think of it as being more difficult. And the problem is this: difficulty is a very subjective term because what I think of as being hard, she might think of as being mad easy, and vice versa.
What?
It's true in both cases, the other way around. That's
No,
okay.
I know what vice versa means. It's just I'm surprised that I think something is easy when you think something's hard.
It's different for everybody. That's the point. Okay. Everybody comes in with a different skill set, a different frame of minds, and all that kind of things. So you have to understand that again, difficulty is so there's nothing about this that says that it's more quote unquote difficult than the next person. Now the thing is this from a depth perspective in terms of how much you have to physically do,
look,
of how much.
This is the frame of mind. What's person?
Wait.
Frame of mind.
Wait a minute.
Frame of mind.
You should have drawn a brain. Why did you draw a person? You should have drawn the brain if you want a frame of minds.
I was pointing to their head. A frame of head. Wait, what?
It's a head frame or a headboard, but we're not. No, I would call that a headboard then, but that's not. But you're not. But you're not. But you're not. No. Headboard is at the front of your bed.
Oh.
Never mind.
Oh gosh, you can barely see.
The point is this. Okay. The key, as I'm saying, is that as far as the amount of calculations and work that you have to do to solve a particular problem, can a particular type of problem have a lot of depth to it and stuff like that? Absolutely. But the depth does not necessarily make it any more difficult. If you take each piece of the process and you micromanage it down step by step into the individual calculations that it involves, then you'll see that each individual step is not quote unquote difficult to do because it's calculations you've done your entire life. You know how to multiply numbers. You know how to add numbers. You know how to do all those things. Even squaring, which you know is a form of multiplication, you know how to do those things. So it's just a matter of just making sure that you go through all those individual calculations, however many there might be, and just making sure that that everything is accurate, that you're not making any mistakes along the way. As long as you do that, it's fine. It's simple enough to do. It's just, again, so don't come in with a precept that it's like, okay, I've got to do all this work. It's so difficult or whatever. It's not if you give yourself a minute to think about it. I know. I can see you. I can see you. Okay.
And I add a little face. His face makes it cute.
Of course it does. Naturally. But that's how you do it the long way. All right. Our Dutch friends, I hope you see this and get everything chimed in there. All right. So we got that. Okay. Let's move on to something a little more low key and stuff like that. You were getting all hyped and excited because you're like, oh, now you're finally adding decimals. Okay, and I know we've done it a little bit here and there in past streams and stuff like that or whatever. But here, let's get you formally in place there. Okay, here I'll give you the marker. Write one of your questions. Write one of your questions in on the math trainer and stuff like that, and let's see how
I don't know.
Let's see how you navigate.
Probably not.
But mute the volume. Come on.
And how am I supposed to tell what they're? Oh.
You could read it.
No, but I can't tell what he's saying. Wait, it's muted.
You know the deal.
Wait. Oh, wait, can you use closed captions?
Okay, but you should.
Hooray for closed captions! Hooray! 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 Doesn't even look like I'm clapping. It just looks like I'm waving my hands angrily. I'm waving my hands angrily at you. Ooh! Waka 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 waka.
He's chasing his decimal dots and going through all that business and everything.
Yummy.
So that's the nature there. But I put
And the decimal dots
when it comes to
are
adding and
made of cookies.
when it comes to adding and subtracting decimals, I put all those decimal points in a vertical line with each other for a reason. And that's because place value matters when you're trying to organize these numbers.
I'm kidding. Each decimal dot isn't a cookie, it's one grape. And every one of the big circles is a cookie. So he eats a lot of grapes and 4 cookies.
Why should it be a cookie?
I don't know. The big dot is, those dots are grapes. And the big dots, so those dots are grapes.
I got a better idea.
And then the big dots are cookies.
I got a better idea. These are the munchkins and the power pellets of the donuts. But then again, the donuts don't. The donuts have holes. The power pellets don't. Oh, who cares? We're being particular here. Can you just read your?
But no, I don't.
Can you read your thing and get?
Pac-Man getting fat.
Can you read your thing and get to the problems here?
You don't want Pac-Man getting fat. That's a little too much munchkins and donuts.
Let's go to the trainer here. Get some questions out. Ah.
What?
The thing logs out.
What? Wait, click the Chrome.
Hold on, I gotta go back in the thing.
Should be there. Did you press the X?
No, I went to start the trainer, but you had it model decimal addition. But you had the thing on too long. So you had the thing on idle too long, so it refused to load it. Okay, all right, so put it into place there. Okay, look at the problem that it shows at the top there. Okay, it shows the numbers 1.83 and 2.70. Okay, so video game comedy aside here. Okay, set those numbers up so that you can set those numbers up so you can add them properly. 1.83 and 2.70. Put them in. Go.
Wait, what?
1.83 and 2.70.
We're not.
2.70.
Oh.
Okay, so all right.
Oh,
so notice it's fine. Okay, go ahead. You do the addition. I'll get the paper towel. Okay, I gotta heat excuse me. I gotta heat the soup up here. Here, so explain how you place the numbers the way you did. Have you guys in the audience out there a few weeks back when I needed her to start without me? You're okay. Wait, why did you line the numbers up the way you did? What's the key to it? Come on, you know this. Fred, come on, explain it. You know.
Because of place value.
Speak up.
Place value. Place value.
So keep talking.
Place value.
Talk more about it. You said that already. What do you mean? Explain. What about place value? Explain what that means. You know what it means. Come on. Oh, fine. Why do you get so embarrassed? Why do you always think you're going to be wrong? See, that's another thing I want to make sure you guys make very intention of yourself. Don't always come into something thinking you're going to be wrong. Okay? Just explain it. Just explain it. You you know this stuff out there, folks, a lot better than you think you do. Okay, so do not automatically assume. Yes, you know, you do. You so do know. You said it had to do with place value, and you were right. Look at the numbers that you have. Okay, what positions are these? What place value is these? Speak up. Come on.
The ones.
The ones place, yes. So you lines ones over ones. What are these? Tenths. You lines up tenths over tenths. And what are these?
100.
And you put hundreds over hundreds. What was I'm confused. What had you so anxious about saying that? Really, Brianna? Don't do that. Don't do that to yourself. And don't you guys out there do it either, okay? Really. You can't afford to do that to yourself. There's so much math anxiety out there in this world. You can't let that throw you. The explanations are a lot simpler than you make them out to be, okay? So don't fake yourself out. Just talk your way through it. Explain it. You know it more than you think you do. All right? So yeah, you lines up the place values, so go ahead. So since you have the place values lined up, start moving your way down the digits. Go. Oh, I take half a second. That's good. Okay, so 4.53. Yes. Yeah. The digits, as long as the place values of numbers are lined up the same as they've always been whenever you added together normal integer and whole numbers and stuff like that, all the rules are still in place. You add down, if you get 10 or more, you carry over because you're able to make the next place value, and so on and so on and so on. Okay, so that part is always going to be be in place. So the work makes sense like that. Okay, so the question is that the work okay. So here's the okay. I get what it's saying here. All right, here we'll come back to that in 1 second. We'll come back to that question. All right. Select the decimal addition problem that requires regrouping the hundreds. Okay, so here's the question. Okay, they're showing us 5 additions here like this. As far as I could guess, I believe that this determines these numbers randomly. At least I think it does, for all I can tell. Now when we say regrouping, Brianna, whenever we have to regroup a place value, what are the circumstances? Like for instance, in this question here, which of the place values did you have to regroup? Did you have to regroup the hundredths, the tenths? How come you had to regroup the tenths? Why?
Because
what happened when you added them? Well, it came out to at least 10. Yeah, because remember, it come out to 10 exactly, and that counts as a regroup. Okay.
Oh, yeah.
Yeah, it came out as more than a 1-digit regroup. Okay, so the question wants to know here is, here's a set of 5 additions. In which one of these 5 additions would you have to regroup the hundredths? So in which one of these, when you try to add the digits place value for place value, will you get more than 10 hundredths. Which one? Which one gives you more than 10 hundredths? You betcha, because how many hundredths do you get out of this one? You get 13, so you have to regroup. So you would only keep the 3. You would tack an extra 1 to the 3 and 4, so you get that, and that would be the nature there. All the others come out to less than 10 when you combine that place value in your place there. Okay, so it's good soup. So that's what we got happening there and stuff like that. Okay, just go back and get the first one here, because all right, it's trying to compare the two people's works and say like who regroups and who didn't, so whose work makes sense and whose doesn't, and stuff like that. Either way, you've got the proper answer there. So the one that leads toward that, you know what is supposed to happen there. Now, the one thing we'll just throw into the mix here is that those were simpler because of the nature of the digits that you were adding. They contain the same number of decimal places. Just to show it again real quick, Brianna, what if you have to do something like this? Here, arrange that one vertically. Arrange this one vertically. Take it. Take it.
Oh, sorry.
Take it. Take it. Take it. So if the whole purpose is lining up place value, how would these organize? I'll get him. You just arrange the problem. Explain what. Good. Well, okay, but all right, take the charger. Charger's right there. Take it with you. Almost. Joey, you gotta go draw the plant. No, I told him taking the other room. Everybody's moving in different directions. Okay. All right. So again, line of place values. So here's the problem then. So why does it look? So again, why does it look like that, Brianna, and not like this? Brianna, why does it not look like this? Why would this be wrong? And if the decimal points aren't aligned, Brianna, you got to speak up, talk. Brianna, you're correct. She's still. You are correct. So if the key is then, and if the decimal points are not lined up with each other, then what else is not lined up with each other? The what? Wait, the decimal points determine the what? The place value. Right? Yes. Okay. So, because if you do this, then this one, because this one, for instance, that one, Brianna, in 131 represents what? What place value is this? But this 4 represents the thousands. Yeah, you can't add hundreds to thousands. Everything has to be added to its own thing. So that's why this does not work. So while it's instinctive to just shove everything over to the right, you can't do that. You have to make sure place value goes with place value. So the way she wrote it is the correct thing. Now, if it helps
And
you,
if it helps, you could add a 0
do it.
to make it equal to that.
Go.
There we go. The finest chicken scratch in the world.
No, mine's the finest chicken scratch in the world. You know that.
That mine's the rockiest. That means mine's the rockiest.
You're
Because
silly.
yours is fine, but mine is rocky. Because
Just promise me something, okay? All right. Don't doubt yourself, okay? Please make sure to to not do that, okay? You're getting yourself all tied up in knots there, and for no reason. When you know this, and you keep proving, you prove it time and time again. Why do you get shy on me all of a sudden?
I just get nervous because I'm the only one here. Sometimes, like that one instance on the other show, another live stream where
I know, but even then, you knew exactly what you were doing, okay? You just never had to put it into words before. And I'm sure that's what gets a lot of you guys nervous about stuff too, that you never had to put it into words yourself. You're just so used to just, okay, here are the numbers, this is what you have to do, and you just go and do it, no questions asked. But sometimes you do have to legitimately stop and ask yourself, why are you doing these things? You got to be able to just like mentally walk your way through it and say, okay, this is why I place the numbers this way because I have to make sure that place values line up, that decimal points line up, and all those things, and stuff like that. So be aware of your process. The process you're going to see can play a bigger role than the numbers themselves ever could. So keep that in note for yourself. And again, that will simplify, and if you still insist on thinking this way, make a problem easier to do. So, but remember again, difficulty is subjective. It's all about depth that determines what a problem's worth actually is. But again, break it down piece by piece. I promise you, it'll always make sense, and you can do anything with this that you want to. All right. For right now, little Miss, I'm gonna give little Miss Nervous here a break and stuff like that, and give you guys a break. All right. So because we're gonna close up shop here for the day. Just a quick programming reminder. Like I said, since this is our last week, we're doing 3 streams this week. Our next one is going to be on Thursday at 2:00 or whatever. It's going to be our last formal. It's going to be our last formal live stream in the sense that we're going to be doing like any formal topics or whatever. So really, if any of you watching out there, if you want to get in and get some last minute suggestions, please absolutely jump in and make sure that you see that you get all your questions in, so that we could spell out as much as we can the hour, so that we're involved with this. And then on Friday for our into summer finale on May 22nd, we're going to revisit all of the games that we played during the course of these live streams, little fun and games things. Tell your friends about them, and we'll play interactive with you guys. So you don't have to just watch us; you get to play too. So, and we're gonna get all that. What happened? Did we forget something? She's thinking. She's trying to remember if we forgot something.
Sorry.
Yes.
I'm sorry.
What?
I'm trying to.
Is what you're saying related to me or not?
Uh-huh.
Well, we'll quick get it in, because I want to close. I want to shut down for the day.
Hi. I don't know. I forget.
Maybe she'll remember her joke for next time, folks. All right. In the meantime, we're going to say goodbye for today. We'll see you on Thursday, 2 p.m. Eastern time. New York area. And but please watch us wherever you happen to be, all around this great world. Have a good one. We'll see. We'll see. What? Come on.
Bye.
Oh, we'll see you. Bye.
Flamingo. Bye. Look at a flamingo. I like flamingos.